Okay, so here in this lesson, we're going to discuss and explore what does it mean to be differentiable. So, like the word contains, differentiability contains the word, differential, which implies derivative. So differentiability implies us to think about the derivative, which is the slope of the tangent. So what does that trigger us to think of is the slope of the tangent. So if a function is differentiable, must the function be continuous? Does continuity imply differentiability? All right, so let's revisit that question. Let's just talk about first where a function is perhaps not differentiable, which triggers where the slope of the tangent doesn't exist. Okay, so if I give you this function here, nice polynomial, I can draw a tangent line at any point, and the slope will exist. It may be negative, it may be zero, but the slope or positive, but the slope is going to exist. So then where would slopes not exist? Well, if we look at this function that is not continuous, say at this point, call it x equals 2, this function is not continuous at 2 because the limit doesn't exist as x approaches 2 of f. So if a function is not continuous at this point, then you can't possibly talk about the slope of a tangent line existing there. Because remember that for a derivative to exist at a point, the slope of the secants from the two sides become one tangent. So again, the slope of the secants from the two sides at that point become one tangent. And here that's just not going to happen. So this is at a place of discontinuity. Another place is we know that slopes of vertical lines do not exist. So when we see a line, or sorry, a function that is continuous, but where the tangent line would become vertical is another place of non-differentiability. So we call that a vertical tangent. The slopes of vertical lines don't exist. And another place where the slope of a tangent does not exist is classically at absolute value functions or at a corner point. Because at this corner point, say the slope to this side is maybe positive 2, but the slope to this side is negative 2. So at the very corner is where the function is not differentiable. So to reinforce that, graphically, what do you need to know? Where a function is not differentiable, any point of discontinuity, any place where the tangent line would become vertical. And sometimes they're hard to spot all the time graphically, but here's a tangent line of 0. And here it is getting more and more and more positive. And as that's happening, it's getting more and more vertical. So any place where there's a vertical tangent, a point of discontinuity, and at a corner point, or sometimes we call that a cusp. Algebraically is pretty easy. It's just going to be anywhere where the derivative does not exist. So where the derivative algebraically does not exist is a place of non-differentiability. So again, we're talking about this topic of differentiability, both graphically and algebraically. Graphically, there are 3 locations: a point of discontinuity, vertical tangent, and at a corner or a cusp. Like something like this right here, right there, that's a point of non-differentiability because the slopes of the tangents from the two sides don't become one value. Let's take a look at a few problems. So determine whether the function is differentiable on the indicated values of x. So this is from negative infinity to infinity. This is a polynomial. When I take the derivative, it's 6x minus 4, which is another polynomial. This derivative exists everywhere. Since the derivative exists everywhere, the function is differentiable everywhere and on that interval. Absolute value functions, as you learned your graphs of parent functions, absolute value functions have a vertex. And that vertex is a corner point. And the vertex is always recognized by setting the inside stuff of the absolute value equal to 0. So that vertex is happening at 3/2. So that means on that graph, when x is 3/2, I would have a corner point. Well, that is a point of non-differentiability. But is 1.5 within that open interval from when we go from -3 to 3 and not including 3? And the answer is yes, because this value of x, 3/2, is included between -3 to 3. And that's a point of non-differentiability. So the answer is no. And then over here, I'm going to just take its derivative. And that, I'm going to make this to the 1/2 power. Drop down the 1/2, repeat the x, decrease it by 1, and the derivative of minus x is -1. So what I'm going to do is, got to get used to this now. I'm going to kick this exponent to the bottom. Okay? I could easily see that my derivative does not exist when x equals 0, because that makes my denominator 0, which makes the derivative a d/e. So is the function differentiable on the closed interval from 0 to 4? No, because 0 is being included. When you have a bracket, 0 is included. When we have an open circle, 0 is not being included. So the answer is yes, because of the fact f is not differentiable at x equals 0. And 0 is not included within that open interval. So the answer is yes here, but no here, because the 0 is being included due to the bracket. Now the piecewise functions. In order for a function to be differentiable, it obviously has to be continuous. So if a function is differentiable, must it also be continuous? And the answer is yes. But does continuity imply differentiability? And the answer is no, because we have that classic example of an absolute value function where it's continuous, but there's that corner point, which makes it not differentiable at that point. So the first thing we have to check for is continuity, because if the function's not continuous, it can't be differentiable. So I'm going to check the limit as x approaches 1 from the left of f, and see how that approaches 1 from the right of f. So you can just spot these, Put the 1 in for the x, and I get 7. Put the 1 in for the x, and I get 7. And f at 1 is equal to 7. So the function is continuous. But now I have to take its derivative. The derivative of the top is 6x, and that derivative is just 0 for x less than 1. And the derivative of the bottom is 6 for x greater than 1. Now, in your homework, you need to check that the limit as x approaches 1 from the left of f prime equals the limit as x approaches 1 from the right of f prime. You need to take the limit now, not only of f to check for continuity, but now we have to make sure that those slopes are the same near 1. So when I put 1 into the top piece, I get a slope of 6. From the right side of 1, I also get a slope of 6. So since these slopes are the same, and the function is continuous at 1, this function is differentiable at 1. But over here again, I have to check continuity first. It's the first thing I check for, continuity. So I put in this, guys, e to the 0 is 1, and 1 plus 0 is 1. And 0 squared is 0 plus 1 is 1. And 1 does equal 1. So the function is continuous, check mark. But the derivative has to be found by doing a piecewise function. And the derivative of the top is e to the x plus 1 for x less than 0. And the derivative of the bottom is 2x for x greater than 0. But you now have to write, so practice this, is 0 from the left of f prime and the 0 from the right of f prime. Not f now, but of f prime, because that's f prime is the slope of the tangent line from the left of 0 and from the right of 0. We have to make sure that they are the same. So if you plug this in, you get e to the 0 plus 1, and 1 plus 1 is 2. Now over here, when I substitute the 0 in for the bottom slope, 2 times 0 is 0, and 2 does not equal 0. The slope from the left of 0 of f prime is not the same slope from the right of 0. So therefore, the answer is no. And now this is a classic AP question. Find the values of the variables so that the function is continuous. Again, you just have to know the steps. So whenever you're prompted with this question, it's two parts. The first part is continuity. So I'm going to write that the limit as x approaches 1 of f has to be, in this case, equal to the limit from the right of f, of 1. So I'm going to sub in 1 for x and get n minus 2. So then 1 for x and get k. So there's my equation. I can't solve for m or k until I get a second equation. But to be differentiable, I need to take the derivative of each piece. And the derivative of this top piece is 2mx. And the derivative of minus 2 is 0. Now this derivative, that's k times x to the 1/2. So drop down the 1/2, times it by k. It's just a constant. It comes along for a ride. Repeat the x and decrease that power by 1. And now I've got to sub in the 1 for the x. I'm going to write the limit. So make sure we do our homework well, where we are writing the limit as x approaches 1 from the right and the left of f prime. All those pieces have to be there, okay? Put in the 1 for the x, and I'll get 2m. Put 1 in from the right, and I'll get 1/2 k. Because 1 to the negative 1/2 is just 1. What do you want to do here? Cross multiply and get 4m equals k. Just put this over 1 and cross multiply. I'm going to substitute this in. Always solve and substitute. So m minus 2 equals 4m. I guess I'll subtract m, get 3m, and m is negative 2/3. If m is negative 2/3, then k is 4 times negative 2/3, which is negative 8/3. And number 6, here's a graph of f. Find the values of x for which f is continuous but not differentiable. Well, it's not continuous at 1.5, but it is continuous at, say, 2.5. It's continuous there, but it's not differentiable. So I would say only at 2.5. For what values of x is f differentiable? Well, graphically, I have a point of discontinuity here at 1.5, and as well as at 3.5, and as well as at a corner point. So it's going to be from 0 to x is 1.5, and then from 1.5 to 2.5, and then from 2.5 to 3.5, and then from 3.5 to 4. For what values of x is f not differentiable? At 1.5 and 3.5, because the function's not continuous there, and as well as 2.5, because there's a corner there. And now let's talk about some of these solutions to various problems. So here, We're just to decide whether or not the given function is continuous. I'm sorry, well, first we'll consider continuity, but is it essentially differentiable on that? If the function's not continuous, guys, at a point, you can't discuss differentiability at that point. So this is a polynomial, and its derivative is another polynomial, and that polynomials are continuous and differentiable everywhere. So the answer is yes and yes. In number 3, I'm going to take the derivative. I'm going to drop down the 2/3, repeat the x, and decrease the power by 1. And f prime equals 4/3, but you got to kick that x to the 1/3 to the denominator so you can assess the derivative better. And the derivative does not, or the derivative, sorry, equals a dne when the bottom equals 0. So when x equals 0, it makes the denominator undefined of the derivative. So 0 is a place of non-differentiability. Now I look to see, is 0 anywhere within the interval from -1 to 1? And 0 is within that range. So the answer is no. Is it differentiable from -2 to 0? And the answer is yes, because 0 is not being included because of the parenthesis. So number 3, the function is not differentiable at 0, but 0 is not included here, but it was over here. Easily on this graph, the vertex is at -1. So f is not differentiable at -1 because that's the vertex on that absolute value graph. Now, is -1 within this closed interval? And the answer is yes, so it's not differentiable there. Is -1 included on this open interval from -1 to 2? And the answer is no, so therefore it is differentiable on that because f is not differentiable at -1, but this does not include -1 because of the parentheses. This one down here, quick, the vertex is again at 3/2. 3/2 is within that open interval from -infinity to infinity, so it's not differentiable there. But 1.5 is not within that range. 1.5 is not within the range of 2 to 8, so the function is differentiable there. In number 6, the derivative of ln is 1 over x times 1. The derivative does not, the derivative is a dne at x equals 0. 0 is not included here because of the parenthesis, so it is differentiable there, but it's not differentiable here because 0 is included. In number 7, one of the problems for homework, I'm going to take the derivative. And f prime, I'm going to make this to the 1/2, drop down the 1/2, repeat the inside, decrease the power by 1, which is -1/2, but the derivative of the inside is -2x. So that's that 4-stepper, drop down the power, repeat the inside, decrease the power by 1 times by the derivative of the inside. And I'm going to get, with those two canceling out, -x over the square root of 9 minus x squared. So where does the derivative not exist? When my denominator equals 0. And this denominator equals 0 when x equals plus or minus 3. Now, is plus or minus 3 included here? No, because it's on the open interval, so it is differentiable there. But -3 to 3, it is included there, so it's not differentiable there, guys. It's not differentiable there. In number 9, I've got to check for continuity first. I got this piecewise function. So at x equals 1, is the function differentiable? I'm going to sub in the 1 to check for continuity first. All these other functions, I knew it was continuous on that interval, by the way. But down here, I don't know. So it is 1 from the left, and it is 1 from the right, and the function value at 1 does equal 1. So it is continuous. But to check for differentiability, I got to take the derivative of each piece. So that's 2 for x less than 1. And this derivative is 2x for x greater than 1. But now I have to observe the limit as x approaches 1 from the left of f prime and see how that compares to x approaching 1 from the right of f prime. It's of f prime now, not f. And the slope to the left of 1 is 2, and from the right of 1 it's 2. So my slopes are the same from the right and the left of 1. So this function is differentiable at 1. So the answer is yes. Down here at number 11, I got to check for continuity first, because piecewise functions are a golden opportunity for functions to not be continuous. And all these functions above, I knew by looking at them that they were continuous on those intervals. I just had to check for the derivative. So again, I'm going to do continuity. And the sine of pi is 0. And the cosine of pi, geez, is -1. So the function's not continuous. So we put our hand up and say, no, not differentiable at x equals pi. But because y, f is not continuous at x equals pi. The function has to be continuous in order to possibly be differentiable. So we always know that differentiability will imply continuity, because if it's differentiable, which means the slope of the tangent exists at every point, the function's got to be continuous. But continuity does not necessarily imply differentiability. You always think of that absolute value function. And the next set of directions, I'm going to do 2 of these, 12 and 13. So we got to find the values of the variable, find the values of m and b so that the function is differentiable. So just learn the steps. The first step is it's got to be continuous. So I'm going to write that the limit as x approaches 1 from the left of f has to be equal to the limit from the right of 1 of f. I'm going to write that limit notation out, guys. Put the 1 in for the x, and you get 2. Put 1 in for the x, and you get n plus b. Now for the derivative parts, this is number 12. I don't have enough room on these. The derivative equals, the derivative of constants just 0, and this derivative is -1. This derivative is 2mx, and this derivative is b. Okay? I'm going to sub in the 1 now, but I have to write that out. The limit as x approaches 1 from the left of f prime. Make sure the limit notation is all there. And f prime. This cannot be missing. I'm just going to put in the 1 and get -1. Put in the 1 for x and get 2m plus b. So here are my 2 equations. And it's up to you what you want to do there. You can solve and substitute or do elimination. I guess I don't know. I could do either one here. I can just say here that m equals 2 minus b, and to solve this for m. And then I can have here that -1 equals 2 times 2 minus b plus b. And then just distribute, just good old algebra. -1 equals 4 minus b. Subtract 4. I'll get -5 equals -b. B equals 5. I'm bothered by that. B is 5. I just want to make sure there. I put in a 1 and I got 2. I put in a 1 and I got m plus b. Should have left enough room for these to do the solutions. And that derivative is -1. And this derivative is 2mx plus b. When I sub in the 1, I get 2m plus b. Sub in the 1, get -1. And then I did solve this right, that m equals 2 minus b. So m from this equals 2 minus b. And then substitute the m in over to here. And that's 4 minus 2b plus b. That's minus b. Yep. So then b equals 5. So if b is 5, then m is negative 3. So there's my values. And I'll do number 13 now. I'm going to need some more room here. So number 13 is I'm going to have to handle continuity first. So remember, continuity first, then differentiability. You're just doing the same with limits. So I have to write that out. The limit as x approaches 1, because that's the corner point, or the breaking point, sorry, of the domain. So that's of f, not of f prime. Put the 1 in for the x, and I'll get 1 plus 3b plus 1. So that's 1 plus 3b plus 1. And on the right side, it's going to be m plus b. And you got to get used to this again from Algebra 1. So it's a system of equations. 2 plus 3b equals m plus b. We can't give in to some tedious computation. We got to push through. And then I'll subtract the 3b and get that so far. The differentiability part, I need the derivative. So what's f prime? F prime is 3b plus 2x for x less than 1. And then it equals m. And that b is 0. The derivative of b is 0. It's a constant. So like this derivative real fast is just 2m. But the derivative of, say, a constant m is just 0. But now you have to write out the limit as x approaches 1 from the left of f prime as x approaches 1 from the right of f prime. You substitute the 1 in for x, not the b or the m. So the 1 in, well, there's no x, so it's just m. So m equals 3b plus 2. You got to substitute that into here. Find out some algebra. And then here, b comes out to be 0. Because when I subtract the 2's, I get 0 equals b. So if b is 0, I then substitute that in. And m is equal to 2. So m is 2 and b is 0. And you can check my solutions if you want on doing number 14. Now, for what points is the function differentiable? Well, maybe consider where it's not differentiable. So it's not differentiable at -1 because of that corner point. It's not differentiable at 0 because it's not continuous there at 0. And it's also not continuous at 2. So we got a corner, non-discontinuity, non-discontinuity. So it's differentiable everywhere from -2 to -1, from -1 to 0, -1 to 2, and from 2 to 3. Don't worry about the endpoints. Where is it continuous but not differentiable? Well, it's continuous at -1, but it's not differentiable there. Where is it neither continuous nor differentiable? Well, that's at x equals 0 and x equals 2. That's where it's both of those. And in 16, this here is a cusp. The tangent lines get more and more vertical, so it's not differentiable at that corner point of x equals 0. So where is it differentiable? From -infinity to 0 and from 0 to infinity. Where is it continuous but not differentiable? Is at x equals 0. And it's nowhere near continuous nor differentiable because it is continuous everywhere. And I hope that helps with the solutions to homework number, forget the number, I think, what is it, 24, as well as the lesson. Again, guys, the takeaway is discussing differentiability, and we equate that to mean the slope of the tangent line. But we need to know where a function is differentiable both graphically and algebraically. Function is not differentiable graphically when we have a corner or a cusp, vertical tangent where it would be continuous, and a point of non-discontinuity. Algebraically, how do we find where functions are not differentiable? We set the derivative equal to zero. Equal to zero. We set the derivative to see where it does not exist. Usually you're setting your denominator equal to zero because that's where a derivative would not exist. And that would be an x value of non-differentiability. All right, I hope that helps.